Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. The representation theory of tori is simple because the group is abelian. But what about non-commutative Lie groups? This is the first video of 3 where I want to show you how you can leverage torus symmetry to study the representation theory of non-commutative Lie groups. And I want to start in the simplest case possible, and that's the Borel subgroup of the complex Lie group SL2C. Okay, so SL2C, that's the Lie group of complex 2x2 matrices with a determinant 1. And what I want to do is to look inside there, the subgroup of upper triangular matrices. Okay, so what are those matrices? So of course they're upper triangular, so you have a 0 here. Okay, so to have determinant 1, I guess you have to have inverse elements on the diagonal, so we'll call them zeta and zeta inverse. So this zeta is a non-zero complex number, and in the upper right you can have any complex number. I'll call that z. Okay, so we want to study this, and how am I going to use torus symmetry to do that? So I need to find a torus. So where is that torus? The point is that inside here, we can find a torus. Okay, so this zeta ranges over C cross, which is a torus. Okay, and in fact, if you look at the diagonal matrices inside here of the form zeta, zeta inverse, we will find a copy of this torus. Okay, so that's the torus T. And we're going to use this torus and the representation theory of this torus to study the representation theory of this B. Okay. So this B, it's generated firstly by these matrices, and we need to incorporate the ones where you have something in the upper triangular part here, that's Z. And the way we'll do that is we're going to look at matrices of the form 1, Z, 0, 1. And these are actually, will form a subgroup of this B. And the way I want to write that out, it's actually the image of the injective group homomorphism E from C to B, where you map Z inside C to 1, Z, 0, 1. So it turns out you can check quite easily that this is a group homomorphism. Okay, so it's a morphism, in fact, of complex Lie groups. Okay, and since that's the case, this will generate a subgroup. It's clearly injective, so you'll get a copy of C inside there. Okay, so one of the easiest ways to check that this is indeed a group homomorphism is to be rather clever about how we write this matrix. Okay, what we can do is we can look at the exponential of z times 0, 0, 1, 0. So that's inside here you'll have 0, z, 0, 0. And it's easy to exponentiate that. So what do? You can use the power series version of this. That's the easiest. So you'll have 1, and then you'll have one of these matrices, which is 0, z, 0, 0. So you'll get this one here once you've added those two terms. And you'll find that if you try to square this matrix or take any higher power, you'll get zeros. So that, in fact, is the exponential. And once you realize this, okay, of course, the map z goes to z times this is additive. And when you apply this exponential, you'll map the additive structure here to the multiplicative structure here. So you do indeed get a group homomorphism. Okay, so it's quite easy to see that this Borel subgroup, the group of all these matrices, is generated by this subgroup, this torus here, and this copy of C here. Okay, for example, in fact, it's generated in a very strong way. Every element in here can be written as a product of an element in here and a product and an element in here. So you just need something here times something in here. Okay, so that brings us to the following remark. Okay, so a finite dimensional representation of this B, so let's suppose it's called rho, and it goes from B to GLV, so it's a representation on V. All you have to do is to say, where does rho send the elements of this torus and send the elements of this copy of C? Okay, so what we're going to do is we're going to restrict rho to this torus, and that's a representation of the torus. And we know the representation theory of tori. Okay, so it's equivalent to giving in this case, it's a one-dimensional torus. So you just need to give a z-graded vector space. So that's called the weight space decomposition, which gives you the simultaneous eigenspaces with respect to the matrices inside here, this T. Okay, so there's a weight space decomposition. V equals the direct sum of these Vn. And then you also have to say, what does rho do to all these matrices? So in other words, you're going to look at the composite rho E from E maps from C, and I'll put a little subscript Z to say that I want to use the variable Z for this copy of C. You apply this E, it brings you to B, and you apply rho, okay, to GLV. If you know what this representation of C is, you can put these together to see what rho does on all of B. Okay, so that's the strategy that we're going to employ. So now we need a little bit of Lie theory, and this Lie theory involves what's called the exponential map. So how do you determine, firstly, what this representation is? What types of things can you have for representations of C? Well, here we also have an abelian Lie group. So we can use various methods to work that out. It's fairly straightforward. And in fact, we use a method that's very similar to how we analyzed the representations of a torus. Okay. And in fact, the method that we use similarly used the exponential map, although in this playlist I didn't present it that way. Okay, so we're going to use the following lemma, which tells us what happens. Suppose you have any representation of this Lie group C. We'll use a variable Z here, and this is a representation rho bar from CZ to GLW, say. Well, in this case, how do you determine what that is? Well, it's completely determined by one piece of information. What we're going to do is we're going to look at d rho bar dz at z equals 0. Okay, so another way to write that, if you want to use more sort of manifold language, is it's d rho bar, the differential here, at 0, z equals 0, and you apply this to the tangent vector 1 inside here. So the tangent space of C, of course, is just C itself. So 1 is a tangent vector inside here. And when you apply it to 1, you're going to get something which is a tangent vector inside here. Okay, so you want to think of this as a manifold GLW. Okay, so GLW is a set of invertible, if W, you can identify this with just n tuples in C, okay, with a choice of basis, you identify it with just basically some n by n matrix, okay. So you're looking at the space of invertible n by n matrices essentially here, okay. And of course that's a manifold because it sits inside a Euclidean space. That's a set of all n by n matrices, which is an n squared dimensional manifold, okay, over the complex numbers. And so what you can do is that the tangent vectors will be basically just these matrices, okay. So you can differentiate this and you'll get essentially just a matrix, okay. So the point is that if you're given this, okay, so this is a derivative expression, you can integrate to recover all of rho bar, okay. So in this case, rho bar of z is equal to the exponential of za. Okay, so just to give you a little bit of feel for what happens here, let's just do a simple example which is already given here. Okay, so I claimed here this is an injective group homomorphism, okay, and B sits inside SL2C, which sits inside GL2C, so this is indeed a representation of C, okay. So let's just see what these quantities look like inside here. So if we look at this quantity, what you can do is here's our rho bar, essentially sends Z to this matrix here. And we can differentiate this at Z equals 0. So we differentiate this with respect to Z. You get 0, 0, 0. And in the upper right, though, you'll get a 1. 0, 0, 0, and you get a 1. So that's why you get this 2 by 2 matrix here, okay? And that's why I've written it that way. And so the claim is that since the derivative at Z equals 0 of this map is 0, 1, 0, 0, if you have such an injective group homomorphism, in fact, it has to have this form. Okay, so that's what you have there. Okay, so why is this true more generally? So let me just give you a bit of a feel for how Lie theory works and this exponential map works. Okay, so the way you want to think of this is that what type of information have you been given? Okay, so the way I want to think of this rho bar is I want to think of this as mapping from C to here. So it's kind of like a trajectory. Okay. You want to see as you vary Z, okay, how does this essentially matrix or this invertible linear endomorphism of W change, okay? So at Z equals 0, it's a group homomorphism, Z equals 0, rho bar of 0 is equal to 1. You start at 1 here, Okay. And what information have you been given? You've been given how it changes at z equals 0. So that's rho bar prime, if you like, of 0. It's just some tangent vector inside the tangent space to this GLW. So here's a tangent vector, and one of the things about Lie groups is not only is it a manifold, but it's also a group. And you can leverage the symmetry here by doing what? Well, the group means that giving any group element, okay, suppose you're given another group element over here, right? You can left multiply by that group element, okay? And that will map the manifold, this Lie group GLW, back to itself. And in particular, it will take this tangent space to this tangent space, and it will take this tangent vector to another tangent vector. And you can do this for every single point on this GLW to give you what's called a left invariant vector field. Okay. And the key point is that if you have such a group homomorphism, it will turn out, and I'll show you the calculation over here, how this actually works, is that this rho, you think of it as just a trajectory, is just an integral curve of this vector field, this left invariant vector field. And since you know that at 0, z equals 0, it has to be 1, you know what it is, okay? And it turns out the formula will be this one here. Okay, so let's go through the non-geometric version, okay? So I've kind of explained geometrically why you might expect this to be true. Let's go through the actual calculation. Okay, so what we'll do is we'll look at d rho bar dz, not just at z equals 0, but for all points. We want to see how is this rho bar changing, okay? What's its rate of change? So the way I'll do that is I'll write this rho bar of z as rho bar of z plus 0, but that 0, I'm going to insert a w here. So it's rho bar of z plus w. I want to look at this term. And to differentiate the rho bar at z is the same as differentiating this rho bar z plus w at w equals 0. Okay, so that's what we're going to do. We're going to do d dw of rho bar of z plus w at w equals 0. And why do I do that? Because I have to use the fact somehow that rho bar is a group homomorphism. And this is where you use it. So remember, it takes addition to matrix multiplication or composition of linear endomorphisms. So this is rho bar of z times rho bar of w. And with respect to w, this rho bar of z is a constant, so I can pull it out. So let's just pull this rho bar of z out here. And then now you're just left with this d dw of rho bar of w at w equals 0. But that's this matrix A. Okay, this is the derivative. That's what you see over here. Okay. So here you'll get this matrix A, and there's a rho bar of z that comes out. So there's A times rho bar of z. Okay, so I guess I probably should have been a bit careful. Maybe I should have swapped the order of these so that you'll get A times rho bar of z. Okay, so I guess it depends on how you like to write your matrices acting on the right or on the left. Okay, so so I guess yeah, maybe I should have swapped this, written this as w plus z. Okay, and then the order of these is reversed, and then that's what you have. Okay, although of course these two matrices will commute. Okay, because they're basically the images inside C, so they will commute. Okay, so this is A times rho bar of z. So now you have a differential equation of d rho bar dz. How is rho bar changing? It's just this constant matrix times rho bar of z. Okay, so that's a differential equation, so you can solve it, and we know what the solution is. Okay, it's all scalar multiples of exponential of za. Okay, that's the solution. And how do we fix the scalar out the front? Of course, we know the initial condition, rho bar of 0 is equal to 1. So in fact, there's no scalar out the front here. It's just the exponential of za. Okay, so that's a lot of theory here. Let's go through a simple example so you can kind of see what's going on. Okay, so the simple example that I want to do is, of course, well, here, this Borel is inside SL2C, which is inside GL2C. Okay, and that's basically change of basis of two-dimensional vector space. So it will also act on this symmetric algebra of two-dimensional vector space, or more simply just the polynomials over C in two variables x and y. Okay, so I want to tell you how some G acts on this. Okay, so the easiest way, I'm just going to tell you what G dot X is and what G dot Y is. And the easiest way to do that and to understand where the natural action comes from is to write this as the matrix product X, Y times the matrix A, B, C, D. So basically, what is A, B, C, D acting on X? Well, you just look at, so this is just a 2 vector, right? A row vector. It'll be just the first coordinate of this. So that'll be AX plus CY. And what is G dot Y? What is this acting on Y? It's just going to be BX plus DY. Okay, so you can check that this actually gives you an action of, in fact, this can be anything inside GL2, but we'll just restrict it to B. And that gives you an infinite dimensional representation of B. To get a finite dimensional one is what you do is you realize that, of course, this has to preserve the degree. Okay. I've just told you what it does on X and Y. Okay. And so it also acts on powers of X and Y and their products. Okay. So all polynomials. I'll go through that in more detail in this calculation here. Okay. So how does B act on the degree D homogeneous polynomials in X and Y? So let's just remind ourselves what that is. So that's basically the C linear span of all the total degree D monomials. So that's X to the D, X to the D minus 1Y, all the way down to Y to the D. Okay, so it's a D plus 1 dimensional complex vector space. And that's what you have here. Okay, so just to make sure you understand fully how the action works, let's just see what's going on. So to work out the action of this B, I just have to tell you what the action of the generating subgroups is. Okay, so how does T act? Okay, and then how does all the elements of this form act? Okay, so what's H of zeta acting on X to the I, Y to the D minus I? Okay, so this is one of the basis vectors here. Okay, so how does this H of zeta act on X? Okay, so that's the first thing. H of zeta act on X. So what was this H of zeta? This H of zeta was my notation. Oh, I forgot to write down what H of zeta was. So let's put that in here. That's going to be this term here. Okay. My H of zeta is going to be this zeta 0, 0, zeta inverse. This diagonal matrix with zeta in the upper left, zeta inverse in the lower right. Okay, so this H of zeta, how does it act on this? Okay, so we use a definition here, and here for this G we have a zeta inverse for the A and the D, and zeros for the B and C. Let's see what it does to X. Okay, so we're basically going to multiply this matrix by XY, and the first coordinate will tell you what it does to X. Okay, so that's going to be zeta times X. So X goes to zeta times X. What about Y? So if you multiply this by XY, okay, that's what it tells you to do here. The G dot Y in that case, you'll have 0 plus zeta inverse Y. So Y goes to zeta inverse Y. So this X to the I, Y to the D minus I goes to zeta X, since X goes to zeta X to the I, and the Y goes to zeta inverse Y. So this part here goes zeta inverse Y to the D minus I. So let's expand this out. Okay, so how many X's do you have? X to the I. You have how many Y's? Y to the D minus I. So that's the same monomial you have here, but you'll also have some zetas floating around. And how many zetas do you have floating around? You have I, and then this is inverse, so you get minus this D minus I. So you get I minus negative I is 2I, and you have a minus D. Zeta to the 2I minus D. So what has this element of this torus, H of zeta, which is this element here, done to this monomial? It's just scaled by zeta to the 2I minus D. So that means that this is one of the simultaneous eigenvectors. It just gets scaled by any torus element. And how much does it get scaled by? Okay, how is that a function of zeta? It just raises zeta to the 2I minus D. So that means that it's in this weight space V subscript 2I minus D. Okay, so that actually tells you that this vector space decomposition is actually the weight space decomposition with respect to this torus. Okay, so that's rather nice. Okay, so this calculation tells you that this is a fairly natural sort of decomposition, okay, vector space decomposition to look at, and it really coincides with what you get by looking at the torus action, if you restrict the action of B to this torus. Okay, so let's look at the other subgroup, which is all these matrices 1, Z, 0, 1. Okay, so that's E of Z, and I'm going to let it act on the same monomial. Okay, so what we'll do here is we'll let this matrix act on X and Y, so we have to right multiply by this X and Y. So we have X and Y here. The first corner will be 1x plus 0, so that means X goes to X goes to X, so this X to the I goes to X to the I. And what about the Y? So if you multiply by xy, you'll get zx plus y. Y goes to zx plus y, so this whole term goes to x to the I, zx plus y to the d minus I. So this here is a lot more complicated, and you can see that this E of z, when you apply it here, is no longer a scalar multiple of that monomial. But what we're going to do now is we're going to look at the next part. We're going to look at this lemma, okay? And we're going to look at what happens when we take this action by this this group here, this copy of C, and we differentiate it at z equals 0. So we'll look at this d rho bar, which is the composite of basically you let E of z act on this, okay? We're going to differentiate this with respect to z at z equals 0. So let's apply this to this side here, okay? And what does it do on that monomial? So basically you just take this expression here, and you differentiate it with respect to z and set z equals 0. Now x to the I, that's a constant, okay, so that comes out, and basically you just have to differentiate this bit here. So here you've got inside the bracket zx plus y, so differentiating this linear term with respect to z, you get an extra x pop out. So the x to the I gives you, together with this x to the I plus 1. Okay, and then differentiating this power here, you've got this d minus I comes out the front here, and you also have to reduce the power here to d minus I minus 1. And then, of course, you take this expression, okay, and you have to set z equals 0, so you'll just get y. So that's y to the d minus I minus 1. And what you'll note here is that you'll get now just a single monomial scaled by something. But remember, all the monomials that we said, they're actually some eigenvector, okay? And in this case here, though, you started in this v to the 2i minus d, okay? And now what happens is that you'll get a scalar multiple of a different monomial. This power of x has gone up by 1, and since the total degree is d, that means the power of y has gone down by 1. So you've moved into a different weight space. In fact, the weight space corresponds to the weight 2i plus 2 minus d. Okay. And what I want to say is that this is actually very, very typical behavior, and allows you to sort of see exactly what a finite dimensional representation of B, how you can think about it, okay? So this theorem is how I'm going to encode what happens, okay? So a finite dimensional complex representation of this Borel subgroup of SL2, so rho from B to GLV. What does it amount to given? What type of data do you need to give? Okay, you need to give two things. So firstly, you need to say, how does the torus act? And that just means a weight space decomposition. V equals the direct sum of this Vn. And then all you need to do is to say, how does the image of this copy of the complex numbers act? Okay, so it's a representation of this rho bar, okay? And that's just given by d rho bar dz at z equals 0. That's from this lemma that we see there, okay? So this E is essentially just an endomorphism from V to V. And can it be arbitrary? Well, it can't be arbitrary. And it turns out that you have some precise condition to say when essentially a representation of T and a representation of C can be put together to give you a representation of B. And what is that condition? It's a very, very nice simple condition that's in terms of the weight spaces, Okay, the condition is just that E sends the weight space Vn into the weight space Vn plus 2. Okay, so we see that here, right? If you have a vector inside this weight space V2i minus d, which is just a scalar multiple of this monomial here, okay, you'll land in this weight space here, where now the weight has increased by 2. Okay, so that's rather nice, is that if you want to say, how do you put together these to get you a representation? Okay, it's precisely the condition that E of Vn is contained inside E of Vn plus 2. And as usual, how do you recover the whole representation? You just need to say, what does rho do to this torus, which is just given by the weight space decomposition, and what does it do to this, this subgroup here? Well, remember, we can use this last part of this lemma to say what rho bar of z is. So rho bar of z is this x of ze. Okay. So let me try to explain why it's true. I can't give you the full proof of this theorem, okay, but I can certainly show you where this comes from. So certainly it'll turn out that this has to be true. And with just a little bit more thought, you can actually show that this condition here, if you have this condition, then you can build this representation of B, okay? So the best way to think about it is to return to the easy case, okay? If you want to study representations of an abelian group or abelian Lie group, how does that work? Well, it's quite easy, because what happens is that if you have two commuting endomorphisms, okay, remember that each of the eigenspaces of one of the endomorphisms is stable with respect to the other endomorphism, okay? So what that basically means that if we had these two subgroups were actually commutative, and this were a commutative group, okay? So in other words, essentially you'll have like the product of C cross with C, except so B is not the product of C cross with C, it's a non-commutative group, okay? But if they were, what would be the condition that you would have if you try to do the same setup, okay? Well, in that case, remember this, all these E of Z, and hence also the derivative, must preserve the eigenspaces of the other one. So in other words, E of Vn is contained inside Vn. That's what happens if they do commute. But unfortunately, they don't commute. And what we just need to do now is we just need to look at precisely how they fail to commute. And it turns out that by analyzing the relation of exactly how they fail to commute, we can obtain this condition here, okay? So how do they fail to commute? So let's just multiply them in each order and see how roughly it comes out. So we're going to do E of Z times H of zeta. So what's E of Z? So that's this upper triangular matrix 1, 1, Z, 0. Okay, and this H of zeta is this diagonal matrix zeta, 0, 0, zeta inverse. You just multiply them out, so I guess you get zeta times the first column, zeta 0, and zeta inverse times the second column. So that's Z zeta inverse, zeta inverse. And of course, we want to write it in the reverse order. So I'm going to write now this H0. I'm going to pull out this H0 onto the left, from the left. So I'm going to pull out zeta 0, 0, zeta inverse. So that's my H of zeta. And what do I get? And the point is that they don't commute, so I'm not going to get the original E of Z. And I claim that what you get over here is now 1 zeta to the minus 2 Z, 0, 1. Okay, so why is it that's the case? Let's just multiply this out. You get 1, 0 times the first column. That's zeta 0, zeta 0. And you get, you'll get, zeta inverse 2Z times this term here. So that's zeta inverse Z, that's correct. And then for the bottom right entry, when you multiply these two, you get zeta inverse times 1. So that's that one there. So that's the correct thing. So if you write this out, well, it's rather nice. What you'll find here is that you'll have the H of zeta here. And what you have here now, of course, you'll get some element of the group, but actually, it's still inside this other subgroup. Okay? It's not E of Z. You can't just push the E of Z across. When you try to push the E of Z across, what it becomes is E of, well, basically, it's also got 1s on the diagonal, but up here you've got zeta to the minus 2Z rather than Z. That's the change, zeta to the minus 2z rather than z. So this e of z to the minus 2z is what you have there. Another way to think about this is that if you conjugate this e of z, so you bring this h of zeta to the left over here, so you have h of zeta inverse e of z, h of zeta, you'll still get something of the form e, but it's e of z to the minus 2z. In other words, if you conjugate this element here, or this subgroup here, by something inside here, you'll stay inside this subgroup. So this is in fact a normal subgroup that you have, okay? But when you conjugate with this, it's not going to be the identity, okay? It's going to do something non-trivial. Okay, so here's the new commutativity relation, okay? E of z times h of zeta equals h of zeta times e of z to the minus 2z. Now, the main thing is that it turns out that if you have any representation where you've defined this h and you've defined this e, as long as they satisfy this equation here, then it will lift to a representation of b. This is the key point. Okay, this is the only condition to make. Okay, you can't have h and e completely independent. Okay, you can't just define an arbitrary representation of the torus and an arbitrary representation of this C, okay, and assume that they will give you a representation of B, basically because this relation holds, okay. But it turns out that, and this is quite easy to say, if you look at how these two subgroups generate B, okay, that if you have this relation holds, okay, then it will define a representation of B, okay. So what we're going to do is we're going to look at how to encode this relation using the new data of weight spaces and also this E here. We're going to encode this equation. So what we'll do is just look at this as a function of z. We'll differentiate with respect to z and set z equals 0. And that'll be our new equation. So let's see what happens over here. So this is h of zeta, it's just linear, so that's what you have here. And it's fixed with respect to z. So we'll just get, when we differentiate e of z, z equals 0, and let that act on the vector space, you'll just get the action of e. On the right-hand side here, so the h of zeta, that's now something linear that you do afterwards. But when you differentiate this with respect to z, this is where you get something different. Okay, so you have to differentiate this z to the minus 2z with respect to z. So that gives you a z to the minus 2 coming out. And that's an e. So again, you get something very similar to what you see before. E times h is almost equal to h times e. Okay, that's what would happen if these two subgroups commuted, but they don't. And the failure of commutativity now, when you do it in this differential form, is just that there's an extra zeta to the minus 2 here. Okay, so let's see that this is the equation that essentially precisely corresponds to this star condition that I've got here. Okay, so let's just see what happens. So let's just pick some little v inside this Vn. Okay, so that's some eigenvector. Okay, and apply this equation to it. So when you apply this equation, h of zeta, how does it act on this v? That's an eigenvector, and so it gets multiplied by zeta to the n. It's inside Vn. The weight here is n. So it's z to the n v. And you apply e to that. On the right-hand side, what's going on? So you apply e to it. Then you multiply by z to the minus 2, so I can bring that out. And then to that ev, you're going to apply h of zeta. Okay, so what we want to do is we want to look at this ev, and we want to say, basically, this ev is inside here. So we want to say that it is an eigenvector. So we want to know, how does h of zeta act on this ev? So that's this term here, right? That's this term here. So we put this z to the minus 2 to the other side, and then we'll see. So this is scalar z to the, so you've got h of zeta dot ev. What is that? The zeta to the n comes out, and you can multiply by zeta squared. So that'll be zeta to the n plus 2 times ev. So here we have it, okay? How does h of zeta, the torus elements, act on this ev? Okay, it now scales, instead of by zeta to the n, which is what it did to v, what it did to ev is it still scales this ev, but now by a factor zeta to the n plus 2. And that tells you that this EV is inside this weight space V n plus 2. And that gives you this theorem, okay? So this is a very, very common sort of technique that you see when you want to try to study the representation theory of a non-commutative Lie group, is you try to use torus symmetry. And the way you'll do that is that you'll try to find a torus, the biggest one you can find actually, inside that group. So here we've got one here. And that will immediately say that if you have a representation of that Lie group, so in this case this Borel subgroup here, this Borel group here, it gives you a weight space decomposition. And the analysis here is that now we can have a different viewpoint, a much simpler viewpoint of this representation. All it involves is this simple weight space decomposition of vector spaces. And then you just have one extra linear endomorphism on here. And the structure of this, it's constrained, and it's a very, very simple constraint that respects this weight space decomposition in a rather curious way, rather than just preserving each of these graded components. It maps one to the one which has weight 2 bigger, so it moves them along like that. I hope you enjoyed this adventure in pure mathematics.